Shane Evans is going to take us through an industry case study looking specifically at the Helios deposit. So please welcome Shane.
Thanks, Helen, and thanks to the organisers for the invite. I'll get my presentation happening here. Oh no, good place to start is at the end, isn't it? Let's try again. Here we go. So I'm going to scale things down a little bit. We're going to look at a project that we've been working on within the data set that Janelle's just been talking about. Just a shout out to start with to a few of the guys that have been working on the project with me. Luke Forty from Kinemax has been our geologist, top drill, done the drilling. We got a few other likely suspects out there. Gap did the downhole EM and the surface EM. Atlas Geophysics did the gravity. Miro Geoscience took another look at the downhole EM. Core Geophysics also had a look at the downhole EM. So there's a few entities involved in the project. So thanks to those guys. So yeah, like I said, I'm going to scale things down, and we're going to talk about how traditionally MT's been used as a sort of a crustal scale or lithospheric scale sort of tool or investigating tool, but it can be used at all scales. I guess the problem we face as MT people as you scale it down, you start competing with other techniques for the near surface investigation like EM and seismics and stuff like that. So when you get closer to surface, some of those other tools might be a bit more effective. But we'll give you some examples to start with, and then we'll go into the project. Here's an example of an investigation of a kimberlite. This is the highest resolution I've ever attempted. This is 25-metre station spacing AMT. We recorded for 20 minutes at each site. The geologist sort of gave me a project to do where they said, you can go and do the MT, give us your model, and then we'll show you the drilling results after you've given us an interpretation. So that was an interesting little challenge. This is the model that we came up with. This is over in Botswana. The basic geology is we've got sand at the surface and a layer of basalt and sandstone that's full of water. This will be the red layer here, and then into basement. So I produced this model, had no idea what the geology was doing from the model, but it all became apparent once they gave us the drilling results. Essentially all the drill holes terminated in the sandstone except for the middle one that stayed in this kimberlite sort of basalt breccia the whole way through. So it's a really good learning experience for me on the kimberlite geology as well as what we could do with MT, and it was a good base to work on other research in the kimberlite world. Here's another one where we did a regional MT survey with Mike Dentith and others in Western Australia. This is a line between Hyden and Norseman, investigating different sort of greenstone belts. Is the regional model over on the left-hand side. What we wanted to do is follow up some of these linear features with a higher resolution survey just to see what we could do, what we could pull out of the data. So the regional survey was at 5 kilometre overnight MT sites. We chased it up in here with 250 metre site spacing, sort of a combination of MT and AMT, and you can see that we pull out a lot more information out of the MT data when we do scale it down. And these are ultramafic belts within the Southern Cross greenstone belt, quite rich in nickel. There's a couple of mines along this ultramafic belt here, and you can see that the conductor feature seems to go down to depth and possibly be the conduit to the surface. So just a couple of examples there. So my client Tim wanted to do something a bit risky. Obviously had a bit of money to spend, so he gave me the task of going through all the eyes of data and trying to pull something out interesting, hopefully a Mount Isa style feature, and then possibly chase it up if we could find anything. So this is sort of the adventure that we went on, chasing down a conductor and trying to drill it and explain it, and we're still in that adventure as we speak. So, you know, there's 1,600 sites to sift through, so it was not a small project, but I'll just talk you through the way that I go about things, and we'll see how we go. So the first step was to just run a 1D model on these data. My thinking was that the strike of the geology is predominantly north-south, so we would run 1D models on the north-south mode. Here's just an example from one of the random sites. We can see at the higher frequencies we get the response of the Eromanga Basin, which we think is fairly flat-lying limestone. On the right-hand side we have the 1D responses, or the 1D models. You can do a smooth sort of an Occaming version, or you can do a layered version if you want, to try and map the boundaries best you can. But you've got to be careful with the layered ones. It's really sort of labour intensive. You've got to watch and make sure the fits are right and it's consistent from site to site, whereas the smooth inversion, you can sort of batch it up and let it go, and that's a sort of quick and easy way to go about things. So that's what I did to start with, and what we're really looking for is sort of conductive features. Just bear in mind that this is a logarithmic scale in the depth here, so we're looking for conductors in this sort of range here. And then on the side you have windows of the layered model as well. So what we can do is we get the results of your smooth 1D, and you can stitch them all together into a cross section. You can see this is the top line of the map ISA extension data set. Up on the left, you can see where we are in plan view. So these are the top two lines. This is just the MT data. This goes down to about 3,000 metres, but really we're looking in that top sort of quarter for something interesting. We can see variations in the basin thickness, and then some strange things going on over here. If we add the AMT data in, we can see, I'll just flick between the two so you can sort of see how things change once you put more data in there. Makes it a bit more messy, but you get more information. Just also bear in mind that the vertical exaggeration is 5 as well. So we've really stretched it down so we can bring out these features. So that's the top two lines. I won't go through them all. I'm just showing these as an example. The next line 3 and 4 there from the top, MT again only. You can see some variations in the basin thickness. Then if we just add the AMT data in, and then we get a bit more out of it. So, you know, I went through all the data and tried to pick out things that look interesting that we should sort of have a closer look at. So the feature I did pick out of here that I thought was most interesting, and I did pick a few, was this one here. It's a textbook example of a discrete conductor in 1D. You get this sort of pant leg effect here. It's not the best view. I'll show you another view of it shortly. Here it is here again, of different gridding and slightly different color scale, just to try and bring that out more. But you do have this pant leg response, which is a really nice sort of thing to see. So that sort of jumped out at me, and this then became sort of the focus of our investigation. If we plot the induction arrows, in theory, the induction arrows should point towards conductors and away from resistors. I've scaled these up a bit just so we can see them a bit easier, but you can see that the induction arrows sort of converge around this area and probably indicate that the most conductive part of the model is to the north. Next step, we chucked it all into a 2D model, which seems like a sensible thing to do. We get a nice response here. So we think we're onto something. And if you plot up the location of it on the magnetics, it sits bang on this, by chance, on this structure here. So that was enough for us, Tim, to go and peg this first tenement here and end up picking up the other 2 tenements a year or so later. So this was all desktop study. Now we had to actually go and do something, which was the scary part of the whole situation. We had to try and explain what this thing was. What are the options for us? Is it discrete, or does it have strike extent? If it's discrete, is it going to be something mineralized, some sulfides? Hopefully, that would be the best case scenario. Probably not in reality. Is it stratigraphic? So if it is it a shale? And we're hoping for some sort of Earth-car shale equivalent. There are other options. Paleo channel at the basement cover contact. If it's full of water or salty water, it may give you a similar response. Does the fault give us that response? Is there water along the fault, or is it altered, or does it have graphite in it or something like that? So there's plenty of options. So we wanted to go and find out what it was or what it is. So we decided to collect another 110 sites of AMT. Here's the grid here at 200 metre site spacing. In the top right here, we've got the 2D model, but over the top of it, the black dots show you the locations of a Bostic transform. And what it really does, it just gives you an indication of depth penetration, a bit like the skin depth that NASA was talking about before. And it tells me that we get enough out of the MT data that we're going to cover the top kilometre and get the depth we want. Even in being conservative, let's say we get 60% of this depth, we're still going to get the depth we want. So I was happy to go ahead with the AMT. It's quicker, it's easier, cheaper, and so that we decided to go down that route. Here's down the bottom, we just got a couple of examples of the data. We were using Phoenix gear with the MTC 30 AMT calls, and they usually drop off. You can record all night, but they're going to drop off at 5 hertz anyway. So all the data was clipped to 5 hertz, and that was the limit. The upper limit was about 10,000 hertz. Typically, you get a dead band up the top here, and if you do record overnight, that sort of disappears because you're stacking for longer, and you also get higher signal during the nighttime hours. So that's what we did with the survey. Examples of data there. Here's if we grid up the data. I'm sort of gridding up data in this area because I know that's the interesting area, and we're out of the basin there. So I'm just gridding up the interesting frequencies. This is apparent resistivity, sort of north-south mode on the left and the phase on the right. Nice sort of responses there, and the phase is a bit more coherent. Doesn't look great in the apparent resistivity, but just bear in mind that every site in the survey is being affected by the conductor that is in the middle. If we sort of zoom out and incorporate some of the other regional data, you can see that it's actually is quite anomalous in the big scheme of things. That's just a bit of the ISA extension AMT data sort of out to the right and left there. We zoom out further and incorporate all the AMT data, you can see that feature may go to the south. And then we're probably getting the Georgina basin effects here because we've got one basin on top of the other, and we're just getting thicker cover there. We can keep zooming out, and then we can see definitely down to the south, we're getting a lot thicker cover at that frequency. But I'm sort of digressing a little bit. Induction narrows are always fun to look at. Again, I've scaled them up a little bit just for effect, but the advantage of getting high quality vertical field data is that you can plot these arrows up and they can support what you're talking about or not, and they also tighten up your inversion to a certain degree. And you can see that the arrows are converging nicely on a couple of features, sort of the central north area here. Here's the same induction arrows on that phase grid that I was showing previously, and they do converge nicely. On this point here, pretty much, you could possibly say here, but we think that the biggest response is about at this station, and that does become the focus a little bit down the track. So we threw all that data into a 3D inversion from Diva, and these are the results of that inversion. So I'm just going to swap into 3D mode, Geoscience Analyst, and hopefully we don't fall apart here. Here we go. So here's the 3D model. Just try and make this a bit more pleasing for the eyeballs. We can sort of zoom up and down. We're looking sort of northeast here. We can zoom up and down in that plane. I've clipped out the highest conductivity cells as well, so that emphasises this sort of the middle of the conductive model, part of the model. If we look at the plan view from the top, we can see the nature of the conductor as well. So it's pretty interesting. We thought, what the hell, we'll stick a drill hole in and we'll see what happens. So we decided to go the most conductive part for no other reason that it's the most conductive part. So our first hole is this one here. The colour coding on the hole has the ion response from the XRF. I'm not sure if that's the right one to plot, but it was the best one, the best data set for sort of defining boundaries. So the hole, I think, was about 600 metres in total length. We drilled a lot of limestone and then a fair amount of dolostone, and nothing that would tell us the source of the conductor. So there was a few stressful moments in there trying to explain to the client why we haven't drilled anything shiny or conductive. So we went sort of back to the drawing board and tried to work out why we'd been sort of unsuccessful in our first attempt. We do have the 2D along here as well, so I'll just chuck that up and we can see why things might be going a little bit amiss with that hole. There's quite a bit of difference between the two models, 100 metres or so, but significant. If we leave the 2D on, we think that the 3D, the centre of the 3D anomaly was way too shallow, and we're probably going across the top of it. We sent the data from just this central site off to our colleague Alan Jones, who's a well-known MT guy, who did a 1D investigation. And I just sort of said to him, listen, we think there's a conductor in there. We think it's probably going to be at the basement sort of cover contact, the proterozoic basement contact. What can you do in 1D? Can you do some sort of sensitivity analysis and have a go at it for us? So he came back, he did an SVD, singular value deconvolution analysis, and he came up with, he said that he thought there was a conductor at 507 metres plus or minus 25 metres, which was a pretty impressive go. So that sits at about, let me have a go just a bit shallower, just a bit down here was his estimate of where the contact should be, and then also the conductor. So what we thought we would do for the next hole is just do a vertical one, then we don't have to worry about any lateral movements. I'll put the next hole up here. Here we go. Right, here's the next hole. So we drilled pretty much straight through it, and then, believe it or not, Alan's estimate of where the contact for the cover would be was within 3 or 4 metres, which is definitely outside the range of MT, but it was a very good estimate given that. So again, limestone, dolostone, and then back into very steeply dipping dolomitic shales. Let's see, I'll go back to my presentation. I've got some pictures of the rocks, which will please some of the audience. So this is the shale that we drilled into, a bit of breccia here, so maybe a bit of faulting, and then you can see how steeply dipping it is. A bit of chloritic alteration in there as well. But nothing conductive again, so another source of frustration on my part. But we have learnt a lot, that's for sure, and we decided to sort of pack up for the field season after that and sort of assess what we have. Because the geology was so steeply dipping, we can't really get a sense of the orientation of the geology, so it's really quite tricky to know what to do next in terms of the next drill hole. What we did get done was some downhole EM, and I'll just put on the first interpretation. So this is where we interpret, one of our consultants has interpreted the downhole EM plate. Sort of heartbreaking to think that we were very close even with the first hole and the second hole, how close we may have been. So this is all happening in real time while we're drilling and trying to work out what to do next. So we got all that done, and we've decided to just sort of go home and think about things for a little while. And really, since then we've spent the whole time sort of just getting second opinions on where to go, more expert opinions. So we asked Nick Oliver to have a look at geochem, XRF, and he was of the opinion that we may be in the Mount Isa sequence, which is a good thing. The native B siltstone, he seemed to think that the geochemistry was an equivalent to that. So that was a really positive response for him. But he did also note that we're a long way from Mount Isa, and we still had to be quite lucky to get an Urquhart shale. We also reran the 3D using CGG's code, and I'll flick that up and we'll have a bit of a look at that. Make this a bit bigger so we can see it. Let me close my door, the shed's getting busy. So this is the CGG model. Again, we can zoom up and down here and just have a bit of a look. I think the plan view is probably a little bit more informative because we can then start seeing some changes to the nature, slight changes. And it's also interesting to put up the mag on top of it just to see how it follows some of the mag features. So you can actually see a bit of a kink in it now, and it most likely has something to do with this fault coming through here. The colour scale is not the best. That's why I've clipped out the very conductive bits to give us the sort of the centre of the anomaly. I'll try and get this back on. Targets there. But essentially what it's done is it's made the conductor quite a bit deeper, and probably fits with what we're thinking a bit better, especially with the drilling. And then, so I think it was a pretty positive result. One more thing we did actually do is we ran another 3D model, but we put a tear in where we thought the fault was. So we thought just to try and push the modelling as far as we could to see if it would make our model as accurate as possible. So here's sort of the example, the result, sorry, with the with a tear in it. You can see where the tear is, but it really doesn't make any difference in the big scheme of things. So it was an interesting thing to do, but it's now nice to know that we can do it for other projects. But in this case, I don't think it changes how we interpret or where we're going to drill the next hole. And the last thing we did is got another opinion on the downhole EM. So I'll chuck up some options there. Here's one that fits pretty well, and it's probably my preferred option just because it fits with the MT quite well. We know that it's a long stratigraphic conductor. Here's the second one in red, also fits pretty well. But what we do know is that the conductor is to the west of the drill hole. You know, when you put any of these plates on the other side to the east of the drill hole, it doesn't fit anywhere near as well. So we're now getting some confidence on where we could possibly poke the next hole. So yes, it has been an adventure. Didn't quite go to plan, but we have learned a hell of a lot, and I think it's pretty obvious where we'll go next. Just flip down to the bottom here. So we are yet to know what this thing is and whether it's even big enough to worry about. That's one of the answers we've got to answer sort of soon. Another problem is because the geology is so steeply dipping that we don't really know where the end of our drill hole is. It's nearly 800 metres deep, the drill hole, so it could have wandered significantly because of the steeply dipping nature of the rocks and the slaty nature of the rocks. So we may want to go back there and survey the hole a bit more accurately. We could probably re-enter these holes and use them to go off and interrogate these EM plates. So we sort of need to answer that question first before we go off and maybe extend the survey north and south. It's obvious that the conductor does go off north and south, but if we go south, then the cover is going to get thicker and things are going to get more difficult and expensive to drill. So looking at the mag, it may flatten out a little bit and become a little bit more easier to explore that way. So, but really we're just chasing a bit more technical input on what's the sort of a sensible thing to do without wasting too much money. And that's about it from me. So thanks very much for listening.
Thanks so much, Shane. Really appreciate that. Certainly does sound like an adventure in combining techniques and trying to get the best out of your data. So true exploration. We do have a couple of questions for you. John Anderson is saying, it looks like a basement high. Did you look at the basal cover for dispersion clues?
It does look like a basement high. I did not look at the basal cover for dispersion clues. No, I didn't. But we're open to any advice that anyone's willing to give us. So thank you.
And Mark Duffett says, Shane, the conductor seems to be within hundreds of metres of the magnetic highs. How deep are these sources thought to be? Presumably they are the Eastern Creek volcanics. What might this imply for the possible volume of potential host strata?
We have tried sort of unsuccessfully to model the magnetics, and actually I was trying to get some dip directions or something from the magnetics, and we didn't really have much success there because we had 400 metres of cover and the line spacing was 400 metres and pretty coarse. We couldn't really get much out of it. So really these questions and more advice, I think.
Well, I have a question. When are you drilling again?
I'm not sure. Soon. When we can get out there, I guess. If I'm being realistic, it'll be next year.
Yeah, it's a bit difficult this year. All right. Look, we have go on.
May I have a question, because I couldn't type here on this QA to Sean.
Of course. Unmute yourself, put your camera on and ask a question.
Yeah, no, it's a quick question to Sean. Is it a constrained 3D inversion, I mean, for that model, or do you use start from homogeneous half space? It's just a quick question.
Yeah, what I usually do is start from a homogeneous half space.
Mm-hmm.
And if we get reasonable fits, we'll continue on from the reasonable model that we finished with from the previous inversion. So the only real constraint that we put in there was the tear down the track.
I see. Okay, thank you very much.
All right, well, I think we should have all of the speakers put their cameras on now and open up to questions to everybody. We still have, I think Nasser and Janelle have they've been answering the questions while Shane was talking that had come through for their presentations. So if anybody wants to see the answers to those specific questions, please look in your Q&A tab and you can see in the answered section, you can see all of the answers. We had a couple of questions also in the chat. Now, we already talked about data dimensionality. To Shane, it is worth it to use mineral chemistry on your rocks from the vertical drill hole to make the most out of those 2 holes. Some more advice?
Yep, thank you.
Helios Jimenez.
I'll get to write these down.
And a lot of thanks as well to all of the speakers. So I might ask Matt and Rick if they can start promoting everybody to panelists, and then people will be able to speak and ask questions and rather than typing them in the chat and the Q&A, if that's all right. And
can I ask a question while I'm promoting?
Oh, please, Rick, do.
Yeah, I mean, well, I guess I had a couple of different questions. It comes back to I saw, I might have missed when you showed the, showed the drill core with the rocks that Nick had interpreted as being native B siltstone. I guess my question was, did Nick pick up anything that looked like anything to do with alteration or any sort of indication of hydrothermal activity in those samples?
He briefly touched on there was a bit of alteration potentially to do with the faulting, but he didn't make a big deal of it, to be honest.
Yeah, because I mean, it's just there certainly is. I mean, when you look at the Mount Isa system, there's been a lot of information kind of compiled on what its far field expression is. So it'd be interesting to, even if there's not a whole lot of indication, there are trends in carbonate composition, and I don't know if there's any carbonates in the. Yeah, it'd certainly be worth it to do everything you could on those rocks.
Yeah, I might chat to you down the track about what some of our options might be going forward.
Yeah, I'll send you. We put together a little. The first workshop we ran in this program had put together a sort of matrix of all the different things you'd expect to see if you were within 10 kilometers, 7.5 kilometers, 5 kilometers of an ISA type system.
Yeah. But, I missed that one. I saw it was up, and it was a bad one to miss. And
I don't know. This was ages ago, before I even knew there was such a thing as webinars. But the other thing I was going to say is that if it is native B, I mean that there is copper mineralization in the native Bs south of Mount Isa, so it's not it's a good, you downplayed it, but I think it's a very good result if it really is Mount Isa group there in the middle of nowhere. It's going to be very encouraging to a lot of people.
Yeah.
Well, Ron Hackney's just saying, thanks to all the speakers, and Shane, great presentation on the challenges of pushing the envelope. It just goes to show there is plenty to learn from things that don't work as initially expected, and I have a feeling that the risk will ultimately pay off. So, vote of confidence in the technique.
Thanks very much, Ron. Appreciate it.
All right, if anybody needs a drink, go and get one. And then we'll
Good
open it
idea.
up to a more fluid discussion. Pardon the pun. That actually wasn't.
And if you stop sharing, actually, I can do this. Don't worry about it. I'll there.
Rick has ultimate control. Here we go. Oh, now I can see everybody. Well, put your cameras on and we can see you. And if anybody and you can now unmute yourselves and ask questions at will, make comment, give criticism, make suggestions, give Shane advice on where his next drill hole should be.
Into the ore body.
Into the ore body, exactly, right?
Well, that's what we're trying to do with the first one.
Yeah.
Oh, very good. Very good.
You have to build the suspense first. It's not every, for every good story has to have a challenging bit first.
Well, this is how Staveley played it down in Victoria, isn't it? With Thursday Gossan, they drilled a lot of smoke before they. I don't think that was necessarily an MT target, but that was a story of building up suspense before hitting the jackpot. I can see Marina there. Hello, Marina.
Really great talks. I really enjoyed them. Thanks to all the speakers. Fantastic.
Thanks, Brian.
Yeah, I think
Thank
watch
you.
this space.
I would really like to thank NASA as well, because he's gotten up early this morning to join us from Germany, and it was definitely a privilege. And Shane as well, thank you so much for contributing today. And I know that you had to delegate school pickup in order to be able to stick around this afternoon. So also really appreciate that.
Better not to hang out with my kids anyway.
Mine's been in and out 5 times while we've been on this, so it's a juggle. And who else do we have? There are a lot of names here that I don't know. Tim Leonard, you've just put your camera on. Where are you joining us from? Hi, Tim. You're unmuted, so you can talk.
I think he's frozen.
He's frozen.
Yeah, Tim's working for Intrepid in Melbourne, and he's helping us with some of the MT metadata that we're working on. Tim, you're frozen, but we hope to get you back soon. Yeah.
Is there anybody that you'd like to give a shout out to, NASA, that you can see here? Everyone's being very shy today.
I'm going to say hello to John Donahue because I used to work with him, actually in 2 different places, but he's hiding. He's got a picture now. Oh no, where's he gone? He disappeared. No, there he is.
He's unmuted. And David Annette was asking some questions as well. So, oh, John, are you there?
Can you hear me, Rick?
Yeah, I can hear you. I can see you twice.
Well, since you've dug me out, I do have a question for
Oh, great.
anyone in the panel, all 3 of you, and thanks very much. They were terrific presentations. And Shane, I feel your pain there. Boy, I can just see the clients. Like, when these things happen to you, you just want to crawl in a hole and sort of go, oh, well, I've tried my best, and I don't have an explanation. So my question is, tipper, putting out vertical mag coils is a pain in the bum, as we all know. Do we need it? Or if somebody says, I'm not doing tipper, would you burn them at the stake? What are the panels feeling on tipper for an exploration sense? I'm talking that top kilometre looking for a conductive ore body.
Yeah, I would definitely get them if you're looking for a conductive ore body, because you need all the help you can get. So from my experience, getting good tipper data really tightens up your model in the end. So I would recommend getting them, and we get them just by default.
Do you? Right. And I guess if you go to a wider, does it help you if you go to a wider station spacing, so you forego detail in your lateral resolution, you gain that back by having the tipper?
Oh, to a certain degree, but not really.
Right.